The power of G-force. From roller coasters to the Big Bang. Everyone's heard the term G-force, but I'm not talking about a movie or a cartoon. I'm talking about gravitational force. What is it exactly? If you had to explain it in a single video, it would look like this. It's that feeling when you're on a gondola or a roller coaster at an amusement park and your stomach feels like it's ending up in your throat. Your blood feels like it's being drained from your head, and your eyes feel like they're about to pop out of their sockets. That's G-force. But honestly, those examples are nothing compared to what we're about to dive into. There are forces in this universe capable of shattering human bones or flattening a skyscraper like a piece of paper. We'll look at all of them, but first, let's talk about what G-force actually is and how we calculate it. The baseline. 1G is the fundamental unit. It's the force that keeps us and everything else pinned to the Earth's surface. This is our standard. Under normal conditions, we don't even feel it. But the moment you step into a sports car, things change. For instance, F1 drivers can experience momentary bursts of 5 Gs during sharp turns. Think of that as 5 times the standard gravitational force. If you weigh 70 kilograms at 5 Gs, it feels like your body weighs 350 kilograms. On the flip side, at 0 G, you are weightless. This is what astronauts experience in space. However, living with nearly 0 G-force for long periods takes a toll. When astronauts return to Earth, they struggle to even stand up because their muscle mass is withered away. Fun fact, there's a common myth that you get taller in space. It's actually not a myth. Without gravity, compressing your spine, the discs between your vertebrae expand by a few millimeters. You do get taller, but unfortunately, it's temporary. Once you're back on Earth, gravity pushes those discs back together, and you return to your original height. Doing the math. So, how do we calculate this? Let's take the acceleration of a Bugatti Veyron. To find the G-force, you take the change in velocity, divide it by the time it took to get there, and then divide that result by 9.81. Why 9.81? That is the gravitational constant 9.81 ms squared discovered by Newton. It means that if you drop an object, whether it's an elephant or a feather, and remove air resistance from the equation, that object will accelerate toward the Earth's core at 9.81 meters per second every second. Both would hit the ground at the exact same time. For our Bugatti, target speed 100 kilometers per h, which is about 28 ms per s. Time 2.3 seconds. Calculation: 28 divided by 2.3 equals 12 mc squared. Result: 12 divided by 9.8 equals 1.2 G. Even though 1.2 Gs feels like your brain is being pressed against your skull, it's only 0.2 Gs above our normal state. That might sound low, but wait until you hear these next examples. Pushing the limits astronauts. During a space shuttle launch, they endure about 3 Gs, feeling 3 times their body weight. Top fuel dragsters. These pilots experience over 4.2 Gs. Roller coasters. Some advanced coasters hit 6 Gs during tight turns. At 70 kilograms, you'd momentarily feel like you weighed 420 kilograms. Sustaining this for too long causes injuries or blackouts. Jet pilots. These are the true gurus of G-force. During dives or sharp maneuvers, they can hit 12 Gs. They undergo brutal training in machines called centrifuges to prevent G-lock, G-force-induced loss of consciousness, where blood is pulled away from the brain, causing an instant blackout. The record breakers. The highest G-force a human is known to have survived was endured by an American test pilot named Eli Beading. During the Cold War, they used rocket sleds to test forces too dangerous for aircraft. In 1958, Beading volunteered for a test where he hit a staggering 82.6 Gs for 0.04 seconds during deceleration. It's a force that should kill a human instantly. He survived because it was so brief, but even in that split second, many of his blood vessels burst. But even that was topped by IndyCar driver Kenny Brack. During a crash where his brakes locked up at full speed, he experienced 214 Gs. His body felt 214 times heavier, roughly 15 tons. Nearly every bone in his body broke. Track officials literally had to recover bone fragments from his ankles off the asphalt so surgeons could reattach them. Gravity in your home and the universe. You might be surprised to learn that a high G-force environment exists in your house, your washing machine. During the spin cycle, it acts as a centrifuge, generating about 400 Gs to dry your socks. But if we look toward the stars, the numbers get haunting. Take neutron stars. These are formed when the core of a massive star collapses. They are incredibly dense. There are about 2,000 of them in our galaxy. One might have twice the mass of our sun but be only 10 kilometers in diameter. The resulting gravitational pull? 7 trillion Gs. If you placed a steel skyscraper on a neutron star, it would be flattened in a nanosecond. The entire structure would be crushed so small you could fit the remains in your pocket. The ultimate force, Planck acceleration finally. Let's talk about the highest theoretical g-force, Planck acceleration. Max Planck defined Planck time as the shortest measurable unit of time. If you take the fastest speed in the universe, the speed of light, and try to reach it within 1 unit of Planck time, you get a number so large it's almost meaningless to write down. Scientists believe this force has only been reached once in history, 14 billion years ago, during the Big Bang. Similar forces are believed to exist inside black holes, but that's a realm where our current understanding of physics starts to blur. That brings us to the edge of quantum physics. But we'll save that for another time. Thanks for watching, and as always, I'll see you next Friday at the same time. See you then!